Hey, Edward.
What's up, Professor? How you doing?
Good. How are you?
Not too bad.
Hanging in there? 3 more weeks?
A couple more weeks. A couple more weeks.
Yeah. I feel it's tough to say just because you guys are all are virtual, but it definitely feels like it's just everyone's just a lot more tired this semester than normal.
Yeah, it's like sitting in front of a computer all day. It's very draining.
Yeah. Yeah. I hear you.
I
I hear
I
you.
really I really can't wait to go back next semester because like yeah, like it's hard. Like productivity is like honestly is like at an all-time low.
Yeah. Yeah. I hear you. It's the same for me too. Yeah.
Yeah,
It's been such a long year, and it's going to be nice to go back.
yeah. I've been a couple of my professors told me the same thing. Like I'm sure it's not easy for you guys either.
Hmm.
Um, so yeah. Yeah, it's like, sitting in front of a computer to do all the classes and then you have to sit in front of a computer to do all your homework. So, but almost there, I guess.
Yep. Almost there. Yeah, I guess it's good. It's good that they're really pushing for us to go back because this can't be sustained. I think at first it was kind of nice in a way because it was convenient and of course it was safer. But like at this point, like I think we're seeing that this can't be sustained for the long term.
No, it cannot. It cannot. Yeah. I mean, I hear from all the other students too. It's really hard to, it's really hard to, at first everyone was like really up for it. Honestly, like everyone was like excited to be like at home, but it really took a toll after what, like a
Hmm.
year plus.
Yeah, yeah, I definitely agree. Yeah, like last semester, I think. I mean, a year ago, it was hard just going virtual all of a sudden. And I think at
Yeah,
that time, everyone was just kind of more worried about just the health of of themselves and for their loved ones. And then last semester was the first one we did all virtual, and that went okay, I think. But this semester, I can definitely feel like everyone's just really tired of it at this point.
yeah,
Professor, what's the tech elective you teach again?
I teach several, and so I teach
There was
EGME
one that was like
410.
cardiovascular computation.
Oh yes, yeah, yeah. So
I
that's
was kind of curious to what that was about.
yeah. It's a new class, and so this is the first semester that I'm offering it. Kind of still making it up on the fly. Not making it up, but adjusting it on the fly. But it's basically the idea is because a lot of my research background is using engineering tools to study blood flow. So most specifically, have you heard of a computational fluid dynamics, CFD?
No, but I guess I can probably figure it out from the name.
Oh yeah, yeah. So it's basically, I mean, it has its origins in aerospace actually, and so these methods were developed to simulate like basically airflow, like over an airplane wing, like over a rocket ship, things like that. Because normally it's really expensive to like build an airplane, build a rocket ship just for testing. And so there's a lot of money and a lot of research put into developing these digital methods to predict things like you can compute things like lift coefficient, drag, things like that, all virtually, so without having to construct any kind of prototypes. And so 442 basically is a big part of the class is using that same CFD technology to simulate blood flow, because blood flow has a lot of similar issues, not quite the same, but like if you want to measure something, if you want to measure some blood flow, it's not an easy thing to cut someone open and put a probe in there. And so, simulations can offer kind of a lot of the same benefits for that as in aerospace. And so a big project is, I have the students, or I have you guys, I give you guys like a medical scan of someone's blood vessels, and then you construct like a digital model, basically like a CAD file of someone's blood vessels. And then I have you run like a CFD simulation on it and use that to study things like cardiovascular disease or medical devices and things like that.
Okay, so is it more about using, like, what programs would we be using?
So it's a specialized research software. So it's called Spherical, and so it's the software that I used when I was in grad school. It's completely open source, so it's free, and so that's the main one that you'd be using. That, and there's another open source software called PairView, which we use to view the results. Yeah.
Okay. Yeah, because like I don't know, tech electives, I don't really know what I should be taking because like I don't really know what I want to do when I get out of college. And I just spotted that and I was just like, that sounds really, really cool.
Yeah. It's it's a cool class. I mean, it's very different. I mean, that was kind of my idea, was to just give you guys something different that you don't see in like a lot of the other electives. But unfortunately, because so right now it's technically not like the full blown class like added to the catalog and everything, because the way it works, that when you propose a new class, it first enters as like, they call it like a special course, and so it has to go under one more set of reviews. Basically, after I've taught it a couple times, then it'll be reviewed, and then hopefully it'll be added to the catalog then. But how often special classes get offered really depends on just what the other things, everything else going on in the department. So I don't know the next time it might be offered. I'm hoping it'll be offered again next spring, but it really depends on what the department needs at that time.
Okay. So wait, is it offered next fall?
No, it's not. So there's
okay.
Yeah, so we need to plan at the earliest it can show up will be next spring.
Okay. Well, hopefully I'll take it around then.
Yeah, hope to see you there too. I do have another class that, and actually I'm behind on the paperwork for that too, but I have another class planned for the fall, another new class called Engineering Biomechanics. And so it's not quite the same as the blood flow one, because blood flow, we just focus just strictly on the fluid mechanics of blood flow. But this other class, so the number for that is going to be 441. It's going to be focused on like how do we look at things like human movement from like an engineering point of view, like how do we quantify these, like how you move your arm and your posture and like walking and things like that. Mostly design, how do you design like medical devices for that, or just like shoes or things like that to help people move. And so I got department approval for it. I'm behind on the paperwork, so I'm hoping hopefully sometime next week when it's less busy, so I can start that process, and hopefully that'll be offered in the fall as well.
Okay, cool. Yeah, because I'm trying to figure out like, what area do I want to study? So it's kind of like, all right, there's like aerodynamics, there's like manufacturing, and then there's like the medical field, which I always kind of stayed away from because I'm like, that sounds really, really hard, but it also sounds really, really cool.
Yeah, it's an emerging area. I mean, it's definitely not as mature as like manufacturing or those other fields, but I think it's very up and coming, and there's a lot of money that's in that business now too. So that's exciting.
How was your weekend, Professor?
I was good. Yeah, I visited a friend over the weekend, so we went hiking um, down at his place, which is by Lake Forest, and so it was nice. How was yours?
Good, good. I just took an exam this morning.
Oh dang, how did that go?
All right, I want to say.
That's good. Better than bad.
Professor, have you seen like the latest news for like the SpaceX and all that fun
No,
stuff?
no. What's going on with that?
Oh, they done their second crew launch, and so far, I don't know if I already said this, but like their NASA awarded them the lunar contract.
Right. Yes. Yes. Yeah. I think we talked about that last time.
Yeah, and it was kind of neat watching the second crew launch because like now they said there's roughly 11 astronauts in the ISS right now.
Mm. Oh yeah, I saw a video of the new astronauts arriving at the ISS. That's awesome.
I think they said that's like they haven't had that many astronauts since like a couple decades back.
Oh wow, dang.
Off topic question for you is if I have a part, how would I, and let's say I'm running through the simulations either through SolidWorks or Fusion 360, how would I like know what loads to apply for it? Like, will I just have to make an assumption that there might be load here and there everywhere?
Yeah, that's a good question, and I think I think that's one of the more difficult things about running simulations, that you have to come up with those loads yourself. And so most of the time it's going to be based on the physical situation that the part's going to be under. And so if you think about, where is this part going to go, in reality, what kinds of forces and what kinds of loads is it going to experience? And so, if you can measure those loads, or you can compute them to a high degree of accuracy, that's the best thing. But a lot of times, that's not the easiest thing to do. And so, yeah, you would kind of have to make some assumptions. I mean, very educated assumptions. It's not just throwing something random in there about what kinds of loads that it would undergo, what directions it would be, where on the part that it would be acting on, and then apply those as boundary conditions. But the usefulness and the accuracy of the simulation is going to depend very strongly on how you set those loads up. So yeah, it's definitely spend some time thinking about it, and get some feedback from someone on seeing if that makes sense given that part too, because that's going to have a big impact on your solution.
All right, thank you, Professor.
Yeah. Mhm. All right, it's 2:30, so let's go ahead and get started. All right, good afternoon, everyone. All right, how's everyone doing today?
Good.
Good. Tired. We got 3 more weeks to go. So this is week 14, and so we have this week, we have next week, and then the week after that, and then that's it for lectures. So this is if you want to start a countdown, this is the sixth and last time that you'll see me. So you see me twice this week, twice next week, and twice the final week, and then or I guess we have the final exam too, so you may see me for that too. But yeah, we're really winding down on the semester, and I was talking to some people before the lecture, and what a hell of a semester it's been. I think at this point, all the virtual virtual learning, virtual teaching, like it's all just, I think we're all just kind of really tired of it. So, I just want to say that, thank you guys for sticking with this for so long. I know it's not easy. With you guys, I know you guys are taking like a ton of classes at the same time. So, and having it all take place in front of the computer it's not easy. And, and hopefully, we'd never have to do anything like this again. But, I just want to say I commend you guys. I respect you guys. And, I want to thank you guys for coming this far. Okay. So the plan for today is we're going to continue our lecture notes on radiation. So radiation is kind of the last big topic that we have to cover in this class. Relatively speaking, relative to the depth that we went into with conduction, convection, we're going to take a very kind of very, very shallow look at radiation, because it really goes a lot deeper than this. But the goal with this section is to kind of just introduce all the main concepts to you, just so that you kind of take this as a foundation. And if you're interested in, and especially if you're going to like aerospace or something, you can take this as a foundation to learn more about radiation that you can use in practice. And so relative to conduction and convection, we spent about, I would say about a little bit over 6 weeks each on those. We're going to spend about half the amount of time here on radiation, but I think we'll get a lot of good information in. We'll get a lot of good concepts in, so you can really take this to the next step if you're interested. Okay. And so another announcement I want to make. So last time we met was last Wednesday, and of course you guys took the midterms then. And so I haven't looked at the midterms yet because I'm kind of behind on a lot of other stuff. And so normally what I like to do is I like to finish grading midterm exams a week after the exam. But with the way things are shaking up this week, I don't think I can get it done by Wednesday. I'm going to try, but I think what's probably more realistic is that I'll have them done by Friday. Okay, and so that's kind of my plan right now. Because just there's a lot of other stuff I have to kind of catch up on, because last week was a lot of administrative meeting stuff happened last week, and so last week was kind of not a good week for getting work done. So this week I'm kind of catching up, but by Friday I should have your exams graded, and you'll know what you'll have by Friday. Okay. So any questions on anything before we get started today? Okay. All right. So let's go ahead and pick up where we left off last Monday. And so it's been a while. So let's go ahead and kind of remind ourselves, just a little bit of just kind of the main points from that last Monday meeting, and then kind of pick up the derivation we left. And so we're on a set of lecture notes called Introduction to Radiation. Right. And so radiation, remember, is the last mode, or the last modality of heat transfer that we've yet to cover. Right? And it's very unique compared to the conduction and convection, whereas where radiation does not require any kind of medium. Okay. Okay. And so it doesn't rely on molecules of matter like conduction and convection does. And so radiation, the way that it transfers heat is through electromagnetic waves. And to kind of give you an analogy or something to kind of ground this discussion in, when you think of when I say electromagnetic waves, think about the way that light travels through space. Okay. Okay. Like when you think about light that's traveling, right? So you think of like the brightness that comes from the sun that hits on the earth, right? There's no matter that's in the space in between Earth and the sun. And so in order for light to make it to the earth, it has to travel through these electromagnetic waves. And heat transfer via radiation is basically the same thing, where it kind of moves on the same mechanism, where those electromagnetic waves are essentially carrying energy. Okay. And so that's essentially what radiation is. Okay. And so I think the problem that we were looking at, or the derivation that we were looking at right when we left off, was we were looking at radiation intensity. So we're looking at a situation like this. So let's say that we have a small area like this. And then this, and this small area right here is emitting heat. It's radiating heat, and it's radiating heat in a hemisphere around itself. Okay. Okay. Because we know that as long as an object has some kind of temperature, has a non-zero temperature, we know that it's going to be radiating heat. Okay, and so the question that we want to answer here under radiation intensity is that if we have some patch or some other object that's some distance away, okay, and so let me draw a patch here on the hemisphere. Okay. And this patch is, we'll say it's some distance r. Okay. Okay. It's some distance r, and it also it subtends this thing called a solid angle. Okay. Okay. And so if you have some patch that's some distance away from your object, that covers some area, we're interested in seeing how much radiation is that patch feeling. Okay. Because what we said last time was that because we're kind of dealing a lot with these basically kind of optics concepts, geometry and where things are located relative to the other ones, this is going to play a much bigger role. Okay, and so we're going to take basically the geometrical properties here along with the radiation concepts that we went over last time to really describe how much radiation energy is this patch intercepting. Okay. Okay. So any questions on this so far? So this is just kind of a recap from last time. Okay. And so let's do a quick recap of what solid angle means too, because that's going to be key to our discussion. All right. So solid angle, you can kind of think of it as kind of like a 3D 3D extension to a regular angle. Okay, because in 2D, we basically went over these concepts where if you have an angle like this, right? This angle is kind of it's basically a representation for how much arc length is subtended by that angle. Oh, sure. Yes, I can go back real quick. Mm-hmm. Okay. Yep. All right. And so in 2D, when we talk about an angle, this angle is, an angle you guys have seen for many, many years of your education. But, one way to think about this angle is that it represents kind of the length of the arc length, or the arc length that's subtended by that angle. Right? Okay. And so this angle and this arc length are very intricately connected. And so you have a bigger angle, you're subtending kind of a wider length, and you're gonna have a much bigger arc length. If you have a smaller angle, you're gonna have a much smaller arc length. And so a solid angle is kind of a 3D representation of this, where you have I think the image that we drew last time was kind of like this flashlight beam thing, okay? And so solid angle, we usually give the symbol omega, okay? And so if you have kind of a flashlight beam, you know, omega is kind of like a representation for how wide your flashlight beam is going to be. Okay. And so just like with angle, you know, this omega and this area right here are very closely connected. Okay. And so that's kind of the analogy that I want you guys to think about when we're talking about solid angle. Okay. And so if we go back to our figure here on the last page, you know, we have this kind of small area here, or the small patch that's some distance away from our radiating surface, right? One way that we can describe this patch relative to the emitting source is to describe its solid angle, right? And last time, you know, right before we left off, we said that this solid angle for this small area right here is equal to sine theta, d theta, d phi, okay? And so that's the solid angle that we're going to be working with, and that's kind of our launching point here for the derivation, okay? Well, remember, you know, when we're dealing with these kind of situations, we usually work in spherical coordinates, okay? And so this angle right here, I always forget their names, and so I think this is called the azimuthal angle. Okay, I give that the symbol theta. Okay, and then the angle that's in the flat plane here, the horizontal plane, you know, this I give this angle phi. Okay, and that's the polar angle. Okay. So any questions on solid angles or anything up to this point? Okay. All right, and so now let's factor in some more optics into this. Okay, and so let's take kind of the same situation, but let's view it kind of from the side. Okay. And so if you have a situation where, you know, we have our emitting source right here, okay? And then let's say that, you know, we have our surface and our patch, sorry, and our patch is like this, okay? And if we kind of take the perspective from this patch, and so let's say that that patch is like your eyeball, or maybe it's a camera lens, right? And let's say that we're looking directly at our emitting surface. Okay. Right. And so, you know, when you're looking at, and you can try this at home too. So, you know, you can take, you know, maybe like your phone or something, okay? And then I want you to try looking at it from straight above, okay? And then from there, I want you to look at it from an angle. It's a little bit hard to see because our eyes and brain kind of naturally kind of, you know, we have kind of good depth perception. But what you should see is that if we kind of do what's called a projection, and projections basically saying, you know, let's take this kind of 2D image that we see with our eyes and just kind of make that into a 2D, you know, just like a picture, right? And so by projection, you know, if we look at this source from an angle, you know, the effective area that we actually see can actually get smaller. And so you can take this to the extreme where, like, let's say that you take your phone and just view it from the side, right? And so if you view your phone from the side, then you basically see nothing, right? And because you're looking at it from the side. Whereas if you look at it straight on, you know, you see kind of the full area of your phone, okay? And so, we have to take this into account where, if we're looking at our source from an angle, we're not going to optically see, everything. And that's going to affect the amount of radiation that we see, okay? And so if we take this into account, and we say that, the angle here, just like we labeled from before, is theta, right? The amount of effective area that we see depends on the angle theta that we look at it from, okay? Or in other words, what we have to do is we have to take our solid angle from the previous page and then multiply by cosine theta. And that'll kind of give us our effective area for this, for this patch. And so what we have here is we have dA, or the area that we see, or the effective area. This is going to be equal to cosine theta times omega, okay? And then from here we can just plug in from omega, which we had from the previous page. We say that dA is equal to cosine theta, sine theta, d theta, d phi. Okay. And so remember, what this expresses here is this is the effective area that's being irradiated on by the emitting surface. Okay, and so it really depends on kind of the angle that we're viewing it from. Okay, so any questions on this so far? Okay, all right. And so now that we have this expression for the area, let's go ahead and relate this back to heat transfer, and then use that to formally define what we call as intensity. Okay. And so if we kind of think back to what we talked about last Monday, the way that we can compute heat transfer is we make a product of two different things. And so this is just in general, and so this isn't directly tied to the derivation that we're doing. And so we make a product of E and area, okay? Where E, remember, this is the emissive power. Okay. And this has units of watts per meter squared. Okay. And so remember, emissive power is kind of the way that we kind of traditionally quantify the amount of radiation heat flux that's coming off an object. Okay. Okay. And so from here, from this definition, we can define what's known as intensity. Right? Okay. And so intensity is defined as the emissive power divided by the surface area of the hemisphere at some distance. Because if you think about all points that are kind of equidistant around an object, you know, it forms a hemisphere, kind of like what we talked about last time, right? And so our intensity I is defined as E, which is our emissive power, divided by the area of the hemisphere. Oops. Okay. And so if we solve this equation for E, then what we get is E is equal to intensity times the area of the hemisphere. Right? Okay. And this is key here because what we're going to do here is we're going to take this E, or this expression for E, plug it back into this expression up here, and then for area of the hemisphere, we can use our solid angle for that. Okay. And so that's how all this is going to be connected. Okay. Because the area, you know, the area of some object within a hemisphere, it's going to depend on its distance, and it's going to depend on its solid angle, okay? Which we have expressions for from the previous slide. Okay, any questions on this? Okay. All right, and so if we put all this together, right, then what we get is Q is equal to I, which is the intensity, times A1 times a hemisphere. Okay. And so there's two areas here, and so you have to be kind of careful about how you, you know, kind of about the differences between them. Okay, so let's start with A1. Okay. And so A1 here, this is the area of the emitting object. Right. And so the object that you're considering that's giving off the radiation, A1 is going to be the surface area of that, right? And so as an example, you know, we always talk about the sun being kind of the biggest source of radiation, you know, that's at least relevant to us here on Earth, right? And so if you're talking about the heat transfer from the sun, A1 here would be the surface area of the entire sun, because that's the thing that's actually emitting heat, okay? And this A hemisphere here, this is basically the area of the object that's receiving the radiation. Okay. And so let's take kind of just the simple case where let's say that we're going to consider the entire hemisphere. Okay. And so this is kind of rare, and so a lot of times you're not going to use the entire hemisphere for this. So let's just, for example, let's create a dome around our object, and then compute the area of the hemisphere from that. And so from that, we have a hemisphere. Okay. This can be equal to integral from 0 to 2 pi, integral from 0 to pi over 2 of our dA that we found from before, right? And so it's be cosine theta, sine theta, d theta, d phi. Okay. Right. And so this is actually an integral that you can evaluate. It's not a fun integral, so you have to do kind of some u substitution. But if you actually perform this integral here, then you get an A hemisphere is equal to pi. Okay. Right. And so if you think about the total emissive power, remember we created a dome around our object, and so that dome is going to catch every single piece of radiation that comes out. Okay, and so for a dome which catches all the radiation, okay, what we can say is that the E, which is the total emissive power for a hemisphere, this is going to be equal to pi, which comes from a hemisphere, times IE, where the IE here is the total intensity of the emitted radiation. Okay. Right, so that's kind of this is kind of the maximum. So this is the maximum where if you have a dome that catches absolutely everything. Okay, so for most cases, you're not going to have the entire dome, and so you're just going to have a small object or a small patch, and that small patch is going to subtend a certain solid angle. Okay, and so on the next page, I'll show you how to modify this expression here for a smaller area with a much smaller solid angle. Okay, so any questions on this so far? Okay. All right, and so now for a smaller patch. Okay, with and so let's say that we have a smaller patch with solid angle omega, then what we can do is we can replace that pi with an area for that solid angle. And so in those cases, the total emissive power is going to be omega times IE times cosine of theta. Okay. And then from this, we can compute the heat transfer. Okay. By just taking E and multiplying it by A1, right? Okay. And so the heat transfer is going to be equal to omega IE times A1 cosine of theta. And so this is radiation heat transfer. To a small patch. Away from some emitting surface. Okay, and so that was a lot of angles and a lot of different stuff going on. And so, next thing I wanted to do is I wanted to do an example just to kind of show you, how all of this kind of fits together. Because right now, it's a lot of different equations, and it's it's a little bit I know it's a little bit hard to kind of grasp what's going on. So hopefully from an example, that makes things a little bit more clear. Right? Okay, so any questions on this before we jump into an example? Okay, so let's look at an example and see how this all of this kind of comes together. Okay, and so let's say that we have an emitting surface with an area of 10 to the minus 3 meters squared. Okay. And so emphasis on emitting. And so this is the object that we're going to assume is putting out the radiation. Okay. And so that's its surface area. So it has an A1 of 10 to the minus 3 meters squared. And let's say that it's emitting with a frequency of 7,000 watts per meter squared. Okay. All right. Oh. Remember the units for a solid angle is steradians, and so we need to add an SR down here too. Okay. All right. So the units for intensity are watts per meter square, steradians. Okay. Okay. And so the radiation from this surface is going to be intercepted by two other surfaces. Okay. Okay, and we'll call them A2 and A3. Okay. And so I'll draw the figure on the next page, but just because we have a little bit of room here, let's state what we want to solve for. Right. And so first of all, we want to solve for, let's solve for the solid angles that are subtended by A2 and A3. And so that's purely just going to be based on the geometry. And then once we have the solid angles, let's compute the rate at which radiation is intercepted by A2 and A3. Okay. And so you can't start this problem without the figure, and so I'll draw the figure on the next page. Before I do that, are there any questions on this example? Okay, so let's go ahead. Let me go ahead and draw the figure here so we can see what we're dealing with. Okay. All right. So the first thing I'm going to draw here is A1. Okay. And so this is the surface that's emitting, and so we're going to put it in kind of the bottom slot, or the bottom part of the figure, okay, to kind of make it consistent with the derivation that we just did. Right? And let's say that we have A2 right on top. Okay? And we'll say that A2 has an area of 10 to the minus 3 meters square, and so it's the same area as the emitting surface. And geometrically, we'll say A2 is kind of right on top of A1, right? And their distance is going to be half a meter, so 0.5. Right. And so that's A2. And so let's say that we have A3 right here off to the side a little bit. And so the area for A3 is going to be 10 to the minus 3 meters squared as well. Distance-wise, it's going to be half a meter away from A1, so just like A2. And then the angle between them, because A3 is off to the side, we'll say that that angle is 45 degrees. Okay? And of course, this is going to be our theta for A3. Okay. And so first thing we're going to do is, now that we know the geometry of the situation, let's go ahead and compute the solid angles. And since we know the distance and we know the area of these patches, and so A2 and A3 are essentially our patches, what we can do is we can just take the ratio or divide the area divided by r squared. Okay. And so this is kind of the simple way that you compute solid angles. You just take the ratio of the receiving surface, excuse me, divided by the distance squared. And so in this case, since A2 and A3, they both have the exact same area, and they're from, and their distances are exactly the same, their solid angles are going to be exactly the same too. Okay. And so even though A3 is at an angle, in terms of area and in terms of distance, they're exactly the same. And so if you plug in the numbers for this, you get 4 times 10 to the minus 3 sterradians. Okay. Right? And so that's the omega value for A2 and A3. Okay. And so now that we know the solid angles, we can solve for the rate of radiation interception based on the following formula. So remember, this is our formula for Q, right? So Q is equal to IE times omega cosine theta times A1, right? And so we know IE because that was given to us in the problem. We know omega for both the surfaces because we just solved for it, okay? We can compute cosine theta. That's pretty simple from the figure. And then A1 is the original area for the emitting surface. All right, so let me do this for surface 2 first. Okay. Okay. And so for A2, if we compute our theta for this one, because it's basically looking right on top of A1, then the theta for A2 here is just going to be 0 degrees. Okay. Okay. And so if theta is going to be 0, then we know cosine of 0 is just 1. And so the heat transfer is just going to be just a plug and chug from here, right? All right, and so we know that the intensity here is 7,000 watts per meter squared times sterradians. Okay. The solid angle, which we just computed up here, is 4 times 10 to the minus 3 sterradians. Okay. And of course, those sterradians are going to cancel out. Then we have cosine of 0, which is just 1. And then we have A1 here, which is the area of the emitting surface. Okay. And so you plug in all those numbers, and what you get is Q on A2 is equal to 28 times 10 to the minus 3 watts. Let me clean that up a little bit. All right. So there's a lot of equations in that derivation, but once you go out and start doing it, it's a lot of this just kind of plug and chug into the right equations. Okay. So any questions on this so far?
I have a question.
Yeah. Mm-hmm.
Why is the angle 0 and not 45?
Yeah, because for this one, we're looking at A2. And so A2 is directly above A1. And so there's no, they're looking kind of right on top of each other.
Okay, thanks, Professor.
Yeah. Mm-hmm. Okay, and so that's A2. And so now let's repeat the calculations for A3. And so for A3, it's the exact same formula, except now the angle, because now we're looking at it from an angle. We're not looking at it right on top. A3 looks at it from an angle. And so the theta for this is going to be 45 degrees. Right? And so we're just going to plug into the exact same formula. The only difference is that instead of taking cosine of 0, now we're taking cosine of 45. Right? And so we plug in for that. We get Q3 is equal to 19.8 times 10 to the minus 3 meters squared. And so you can see it's less. And so if you compare that to Q2 right here, Q2 is a full 28 times 10 to the minus 3. But since A3 is looking at it from an angle, it's not going to get as much radiation from that because the effective area that it sees is smaller. Right? And so that's why for A3 here, even though it's the same distance away, because it's viewing A1 in an angle, it's not going to feel the full force of the radiation. Okay. Any questions on that example? Okay. And so that's hopefully fairly straightforward. But one thing that you should notice from this last example is that A2 and A3, they were kind of optimally turned, right? And so A3 was kind of turned, angled like this, such that it kind of faced, it kind of did its best to look at A1, right? Okay, but let's consider a situation instead where, let's say that we have a new challenger, right? So let's say that we have an A4, okay? But instead of turning towards A1, let's say that A4 is kind of turned off to the side. Okay, and so in other words, it's not going to be facing A1 optimally. And so if we draw a line here, and so let's consider, let's say that it's also 0.5 meters away, but if you draw another line here that's kind of perpendicular to the surface, we now have another angle that we need to account for, and this angle is theta 2. Okay. Right. And so probably, as you can imagine, because this surface is kind of turned away, it's not going to feel the same full force of the radiation as the other two surfaces. Okay. And in particular, what's going to happen is that because this surface is turned away, this theta 2 here is going to affect the solid angle. It's going to affect the solid angle for this A4. Okay. And so, and so in these situations, you need to change your solid angle to account for this. Okay. And so now what we have for the solid angle, normally what we have is A4 divided by R squared. Okay. We need to multiply this by another cosine of theta 2. Okay. Where theta 2, if we can kind of give this a formal definition, theta 2 is the amount that we rotate away from the emitting source. And so let's repeat the same calculation. And so let's say that A4 has the same areas as A1, A2, and A3. But let's repeat the calculation. Let's say that for the following angles. And so we have another example, or I guess this is kind of an add-on to the last example. Okay. And so let's say that we have another surface. And so we'll say that A4 is equal to, or the area for that surface is 10 to the minus 3 meters squared. Okay. Let's say that the radius, or the distance away from the emitting source here, is going to be 0.5 meter, 0.5 meters. Okay. The theta for the surface, which is the first angle, is going to be 60 degrees. Okay. So a little bit different than A3. Okay. And let's say that A4 here is rotated away with an angle of 30 degrees. And so we need to factor all of these guys into account and compute kind of the same things that we've done before. Right? And so first we're going to compute the solid angle for this new surface, and then we're going to compute the heat transfer rate. Okay, and so let me put all that onto the same figure here. So let's say that this theta right here is equal to 60 degrees, right? And so that's kind of the angle for where the patch is physically located. Okay? And then this patch we can say is rotated away, where this theta 2 here is 30 degrees. Okay. All right, and so that's kind of where you see both of those angles for this example. Okay, so any questions on this so far before we run through those calculations? Okay, and so we have all the information here, so we can just go ahead and start plugging it in. All right, so first let's compute the solid angle. And so the solid angle is just going to be A4 divided by R squared times cosine of the rotation angle, okay? So we're rotating away by 30 degrees. And so we plug in for that, and we get a solid angle of 3.46 times 10 to the minus 3 sterradians. Okay. All right, so now that we have the solid angle, we can compute the heat transfer rate, okay, or the rate at which radiation is intercepted. And so it's going to be our intensity times our solid angle times cosine of the of just plane theta, okay, times A1. Okay, and we plug all that in, we get 12.1 times 10 to the minus 3 watts. Okay. All right, and so this kind of hopefully just kind of drives the point home that geometry here is it plays a really big role, not only where things are located, but how they're turned towards your object, because that's going to affect how many electromagnetic waves or light waves that kind of hit your object. Okay. All right, any questions on this example before we move on to the next topic? Okay, all right, so let's go ahead and move on. And so the next topic that we're going to go over is called black body radiation. Okay, and so just to kind of remind you, we went over the definition for black body before. But let's go over it again. And so a black body is basically an object it's an object with perfect emissivity and perfect absorptivity. Remember, emissivity is given by the symbol epsilon. Okay. And perfect emissivity means that it's it's 100% emitting, and so it has an emissivity of 1. Okay. Okay. And the perfect absorptivity is alpha is equal to 1.0. And so, what this essentially means that this is kind of the perfect kind of radiation body that you can have, right? And so a black body, if it's at a certain temperature, there's no object that can emit more radiation or absorb radiation than any of that. Okay. All right. And so, kind of similar to a lot of idealizations that we have in engineering and physics. The idea of a black body or an object with perfect emissivity, perfect absorptivity is just an idealization. Practically, it's impossible to have a surface or have an object that has perfect emissivity and perfect absorptivity, right? And so you can get close, and so you can get emissivities of like 0.999, right? But it's basically impossible to have something that's 1.0 emissivity, 1.0 absorptivity, okay? Right? And so it's very similar to cases that you've probably seen in physics where you say you ignore air resistance or you ignore friction, or you've seen kind of those things before. And so the black body, for calculations, it's really useful because it allows us to kind of focus on some other stuff. But I just want to let you guys know that it's very, very impossible to accomplish this in practice. Okay. And so kind of from this point forward until I kind of say so, we're going to be working with just purely black bodies. Okay. All right. And so, with that kind of established and building kind of on this idea of intensity, what we can do is we can establish an equation for the spectral intensity of a black body. And the equation is a little bit big, and so I'm going to show it on the next page. But before I do that, are there any questions on this? Okay. All right. And so the equation for spectral intensity of a black body is given by the following. Okay. So remember, we have the symbol for intensity. We give capital I. And then we say it's sub lambda and b. Okay. Right. And this is going to be primarily a function of two variables. And so the first variable is lambda. And so lambda, we say that this is the wavelength of the electromagnetic wave. And T, of course, here is the temperature. Okay? And so those are our two kind of independent variables that we're going to consider. And so this equation here is kind of a big one. And so I'm not going to derive this equation for, and you'll kind of see why. But we're going to use this equation for lots of other stuff for the rest of this unit. All right. And so it's going to equal to 2h CO squared. Unfortunately, that H does not mean convection coefficient because scientists love to reuse the same symbols for everything, which makes life worse for everyone else. Okay, and so this formula right here, this is the spectral intensity of a black body, right? And so there's a bunch of new parameters here, and so we have to kind of define all of them. Okay. All right, so let's start with H. And so this H here, unfortunately, is not convection coefficient, because remember, we're not doing convection anymore. But this H is known as a Planck's constant. And so it has a value. And so there's that value is 6.626 times 10 to the minus 34, right, joule seconds. Okay. And this is Planck's constant. Okay. The next constant that we have in there is KB, or K sub B. Okay. This has a value of 1.381. Times 10 to the minus 23 joules per Kelvin. Okay. And so this is the Boltzmann constant. Okay. And we have CO, which is probably the most recognizable one, and this is the speed of light. All right. Usually I see Planck's constant with the line through the top like a T to distinguish it from other H variables. Oh, yeah, that's a good idea. So kind of like that.
So I mean to like intersect the line.
Ah. Kind of like that a little bit.
Just like one line perpendicular to the H.
Uh-huh.
Like right through the H.
Oh, right through the H. I see.
Yeah.
Oh, you mean like this?
Right. Yeah, just
Okay.
one line straight through it.
That's a good idea. All right, let's do that.
I've seen that in a lot of books.
Yeah, let's do that so we don't confuse it with convection coefficient. Yeah, thanks for that, Kit. Okay, and then the last constant we have here is CO, and this is just the speed of light. And so this is a 2.998 times 10 to the 8th meters per second. And this is just speed of light. And just a reminder that, you know, when we're working with radiation, the T has to be in Kelvin, or it has to be in some kind of absolute units. Okay. Right. And so it's kind of a doozy of a formula, and so you know, we're not going to use it for much, but you know, and I'll show you kind of ways to kind of simplify this. But this is kind of the way that we, or this is the expression for spectral intensity. Okay. And remember, it's a function both on temperature and a function on wavelength. All right. And so, you know, you're probably asking yourself, you know, what does wavelength have to do, or where did wavelength come from, and why is that a thing here, right? And so, you know, let's talk about that a little bit. Because remember, you know, radiation is heat transfer via electromagnetic waves. Okay? And remember, the other thing that travels by electromagnetic waves is light, right? Okay. And I know it's probably been a while since you guys have probably seen these physics and optics, right? But if you think about, you know, the light that kind of travels all around us, right? Its behavior depends very strongly on the wavelength, right? And so you have things like infrared light, you have things like microwaves, you have things visible light, you know, ultraviolet, right? And so, you know, depending on the wavelength of the electromagnetic wave, you know, it's going to depend, you know, very differently, right? And so radiation is no different. And so radiation, you know, depending on the wavelength of that heat transfer, you know, it's going to experience different behavior, or more specifically, it's going to have different intensity. Okay. And so that's why we have a wavelength that's in this equation. Okay. And so that's just to kind of, you know, illustrate to you guys that you know, that is going to be a factor. Okay? And another reason why, you know, we're not going to go too deep into radiation, because, you know, you'll see that things can get really messy in a hurry with these kinds of things. So you know, just kind of be aware of it, and we'll do some kind of elementary calculations with it, but you know, in reality, you know, these can be, this can get pretty hairy very quickly. Okay. Any questions on this? Okay. All right. And so, you know, the way this is kind of used in practice is that, you know, if you have a certain kind of object and it's radiating some kind of heat, a lot of times that object will only radiate heat within kind of a very narrow band of wavelengths. Right? And so what we're going to do is we're going to take basically this equation here and evaluate it for what I like to call like a band of different wavelengths. Okay, but before we do that, let's go ahead and take this intensity equation and use it to compute emissive power. Okay, because remember, emissive power, or at least the way that we compute it from intensity, is simply just pi times intensity. Okay. And so if we take our previous expression there and multiply it by pi, then we can get an expression for the spectral emissive power as a function of wavelength and temperature. Okay. And so this is going to be 2 pi C0 squared times Planck's constant. Okay. All divided by wavelength to the 5th power times exponential of HCO divided by lambda KB times T minus 1. Okay. And that's the spectral emissive power. Okay. Okay. And so, actually kind of the more interesting thing is to kind of take this expression right here and plot it for different temperatures. Okay. Okay. And so it's a multivariable function. And so, we have 2 independents. And so we can't just make a plot for everything. But what we can do is we can set the temperature equal to some fixed values and then plot it for that. Okay. And so for the x-axis here, let's have wavelength. Okay. Gamma. Right. And then on the y-axis here, let's have the spectral emissive power, or E. And let's plot it for several different temperatures. Okay. So first, let's do kind of a small one, and so let's do let's say temperature is equal to 1,000 Kelvin. Okay. Okay. I say small, but 1,000 Kelvin will melt your face off. Okay. And let's do a hotter one now. And so it looks like kind of like that. So this is going to be at 2,000 Kelvin. Okay. And now let's do one of the hottest objects that we kind of see every day, and let's do the sun. Okay. Okay. And so this is the curve at temperatures equal to 5,800 Kelvin. And that's the sun. Okay, and so you can see here this graph, obviously it gets higher and higher for higher temperatures, but it also kind of shifts to the left. The peak kind of shifts to the left a little bit. Okay, and then for the sun, what you see is that if we kind of take this band of wavelengths about, okay, which is basically around where the peak is for the sun. This band of wavelengths right here, this is the visible spectrum of wavelengths. Okay. And so that explains a lot. So a lot of the radiation that the sun emits and reaches the Earth, it's among that visible spectrum. And so that kind of gives us life. Okay. Life and allows us to see stuff, obviously. Okay, so any questions on this so far? Okay. All right. and so let's talk a bit about more about the relationship between lambda and t. Okay, and so the relationship between these guys is known as Wien's law. Or in other words, because a lot of times when we look at curves like the one we had on the previous page, we're interested in knowing where the peak of that curve is. Okay? And so we'll call this lambda max. And so what this guy named Wien discovered was that if you take the product between lambda max and t, there's an approximate relationship between the two, where the maximum of the curve, usually occurs around the number 2898 micrometers Kelvin. Okay. And so one way that you can compute kind of the approximate location where lambda max is to, let's say that you have a certain temperature, okay? And so let's take the temperature of the sun, which is 5800 Kelvin, okay? And so if you take this 2898, and you divide it by that temperature, and you can find approximately where the maximum wavelength is. Okay. All right, and so if you do this for the sun, where the sun has a temperature of 5800 Kelvin, okay, what you get is a lambda max that's about almost a half a micrometer. Okay. And if you're curious about where this kind of falls within the color spectrum, this falls within the visible spectrum, and it falls within the range of green. Right. And so if you kind of just purely based on the wavelength that or the highest power wavelength that reaches the Earth, those are kind of wavelengths in the green spectrum, but the sun never appears green to us, right? And so don't look at the sun, don't test this, but the sun usually appears like kind of yellow and orange and red to us, and that kind of effect is due more to kind of atmospheric absorbing of certain wavelengths. So the atmosphere, and so in reality, what color that we see from the sun is actually a very complex process, but just know that the atmosphere and kind of all the constituents in the clouds and all that stuff, that has a strong impact on, what color that we actually see from the sun. So even though the wavelengths at the highest power is green from the sun, because of the atmosphere and things like that, it usually appears kind of yellow and orange and red to us. Okay, any questions on this? Okay, and so at this point, we kind of have multiple kind of definitions for emissive power, right? So we've kind of seen it kind of several times, and so let's kind of pull them all together because they all represent the same concept. It's just that there's just kind of different ways of expressing it. And so remember from a week ago, we had an equation for emissive power that looked like this. Right? And so emissive power was sigma times t to the fourth, right? Where this sigma here, remember, this was the Stefan-Boltzmann constant. But just now, I told you that we have a different definition for emissive power. Okay? I told you that E of lambda t is equal to 2 pi c naught squared times Planck's constant divided by lambda to the fifth times exponential of HCO divided by lambda kBt minus 1. Okay. All right. And so how do these two actually connect? Because they actually do represent the same thing. Okay. And so the way that you can connect these two is to note that the first expression here doesn't depend on wavelength, right? There's no wavelength that appears for that, but in the bottom one, we do have wavelength, okay? And so the way that we relate these two is that we take this expression on the bottom and we have to integrate this over all possible wavelengths. And so we're going to take this expression here and basically integrate it from 0 to infinity, okay, times d lambda, right? And of course, this is a nightmare of an integral. And so if you're really masochistic, you can try to evaluate this integral. I'm not, and so I'm going to take, and so I've actually never evaluated this integral before. I've kind of just taken the book's word for it, right? And so if you supposedly, and if you evaluate this integral from 0 to infinity, and of course you'd have to use some asymptotic method to get to the infinity from there. What you should get is you should get the exact same expression that you got above. And so the relationship between the two is that you can think of the original expression, that sigma t to the fourth, as kind of the total emissive power from all wavelengths. Okay. All right. So any questions on this? Okay. All right. And so we're just about out of time today, and so I'm going to go ahead and call it here. But next time, what we'll see is that we're going to work on this expression here on the bottom. Okay. Because a lot of times, we're only interested in evaluating this emissive power just for a band of wavelengths, right? And so a lower bound of certain lambda and an upper bound of a certain lambda. Okay, a lot of times we're not really interested in the full, integral from 0 to infinity. Right? And so what we'll do next time is, I'll show you how to take this expression here, integrate it for just kind of a set band of wavelengths, and how we can actually use that in practice. Okay. All right, and so we're out of time for today. So thank you guys for tuning in. I don't have the next homework for you guys ready, but I should have it ready by Wednesday. Okay. And your midterms I'll grade by Friday. So have a great day, everyone, and I'll see you guys on Wednesday.
Thank you, Professor.
Thanks, guys.
Thank you, Professor.
Thanks, guys.
Professor, one question for you.
Sure.
For the homework that I turned in late, it will still get graded, but just at a later time.
Correct. I haven't graded the homework yet. I'm kind of behind on everything, but I want to grade your guys' midterms first because I think you guys are more dying to find that out first, and then I'll grade the homeworks after that. So the homeworks might not be graded until next week.
Okay, thank you.
Yeah. Mm-hmm. Hamad, did you have any more questions? Okay. All right. So if you don't have more questions, I'm going to go ahead and end the call. So have a great day, and I'll see you on Wednesday.